In the United States Treasury, silver did not exist as metal. It existed as certainty. By 1942, the nation's silver reserves were not measured emotionally or symbolically. They were measured in ledgers, vault inventories, and troy ounces, stacked in precise, identical bars behind thick concrete walls at the West Point Bullion Depository. Each bar weighed exactly 1,000 troy ounces. Each bar was stamped, recorded, audited, and guarded. Together, they represented monetary stability, institutional trust, and the physical backing of a nation at war. Silver was not raw material. Silver was untouchable. That assumption had never been seriously challenged. Not during the Great Depression, not during rearmament, not even as the United States began mobilizing for global war. Factories consumed steel, aluminum, copper, rubber, oil. Silver remained where it belonged, silent, inert, and inviolate. Until one morning in Washington. The request did not arrive dramatically. There were no flashing alarms, no urgent cables marked highest priority. It came in the form of a scheduled meeting, quietly arranged, involving a young Army officer and senior officials of the Treasury Department. Lieutenant Colonel Kenneth D. Nichols was not a man who looked like he belonged in that room. He was an engineer by training, not a financier. His experience lay in construction, logistics, and problem-solving under pressure, not in monetary policy or precious metals accounting. He wore a uniform, carried a folder, and spoke plainly. There was no attempt at persuasion, no rhetorical flourish. He had come to ask for silver. When Nichols stated the number, the room fell silent. 6,000 tons. Not pounds, not bars, tons. The Treasury did not think in tons. It thought in troy ounces, small, precise units used for weighing precious metals. The scale Nichols had introduced did not belong to their world. It belonged to railroads, shipyards, blast furnaces.
As you can see from this chart, gentlemen,
it belonged to industry. Assistant Secretary Daniel W. Bell leaned back slightly in his chair, studying the officer in front of him. 6,000 tons, Bell repeated. How many troy ounces is that? Nichols did not answer immediately. Sir, he said finally, I don't know. It was not ignorance. It was incompatibility. Two competent men, each expert in his own domain, had collided with a problem that existed between worlds. The Treasury's universe was built on precision and accounting. Nichols' universe was built on scale and urgency. They shared no common unit of measurement. Bell's expression tightened. Young man, he said, the Treasury will always think in troy ounces. Nichols did not argue. He could not explain. The project he represented was so classified that even the guardians of the nation's wealth were not permitted to know its purpose. He could not say what the silver would become. He could not say why it was needed. He could not say what failure would mean. So he repeated the only thing he was authorized to say. 6,000 tons, he said again. Then more quietly, we need it immediately. That was the moment Bell understood that this request was not negotiable. Whatever this project was, it existed above normal process, above departmental boundaries, above precedent. It was not asking for permission. It was announcing necessity. Bell took a breath. All right, he said. We'll approve the transfer. At the time, no one in that room understood the full scope of what had just been set in motion. because 6,000 tons was not the real number. As plans evolved, engineers recalculated, designs expanded, prototypes grew larger, entire facilities were added. The requirement climbed relentlessly. 7,000 tons, 10,000, more. By the time the final specifications were complete, the true number had crystallized. 14,700 tons of silver. Silver that would not be stored, loaned, or displayed. Silver that would be melted, extruded, shaped, wound, sealed, energized, stressed, and buried inside machines the size of buildings. Silver that would cease to function as wealth and instead become infrastructure. This was not monetary policy. It was industrial desperation. To understand why the United States was willing to melt down a significant portion of its national silver reserve, it is necessary to understand the problem that forced the decision. A problem so deceptively simple that it could be explained in a single sentence, and so brutally difficult that many of the world's leading scientists believed it might be unsolvable in time to matter. If you wanted an atomic bomb, you needed uranium-235. If you did not have uranium-235, you did not have a bomb. The physics was settled by the late 1930s. Uranium-235 could sustain a fast neutron chain reaction. Uranium-238 could not. Everything else followed from that fact. There was just one problem. In nature, uranium-235 makes up only 0.72% of all uranium. The remaining 99.28% is uranium-238. Chemically, the two isotopes are identical. Same electrons, same bonding behavior, same reactions. To a chemist, they are indistinguishable. Their only difference lies in the nucleus. Uranium-235 has 143 neutrons. Uranium-238 has 146. 3 neutrons. That infinitesimal difference determined whether a lump of metal was useless ore or the core of the most powerful weapon ever conceived. The Manhattan Project needed uranium enriched to at least 90% uranium-235. There was no known natural source. There was no chemical trick, no filter, no shortcut. Atoms had to be separated one, by mass. No nation had ever done this at industrial scale. Most scientists believed it could not be done quickly enough to influence the war. Several methods were proposed. Gaseous diffusion, which relied on forcing uranium hexafluoride through barriers with microscopic pores. The theory was sound. The engineering was nightmarish. No material existed that could withstand the corrosive gas while maintaining uniform pore size. Thermal diffusion, which used temperature gradients to separate isotopes. Promising in principle, unstable and inefficient in practice. Centrifuges, which exploited rotational inertia. Elegant, fragile, years away from reliable mass production. None of these methods offered speed, and speed was everything. No one knew how close Germany was to solving the same problem. Intelligence was fragmentary. Estimates varied wildly. The only certainty was that time could not be wasted. That was when an idea surfaced that was neither elegant nor efficient, but might be fast enough. It came from a man who had already built machines most physicists considered excessive. Ernest Orlando Lawrence. Lawrence was not a theorist in the traditional sense. He was a builder, a machine physicist. He believed that if physics permitted a process in principle, engineering could force it into reality through scale. His invention, the cyclotron, had already transformed nuclear physics by accelerating charged particles in circular paths using magnetic fields. Lawrence understood something fundamental about mass and motion. He also understood magnets. In 1941, British physicist Mark Oliphant visited Lawrence at Berkeley with news from the United Kingdom's atomic research efforts. A bomb was possible, Oliphant said, but only if enriched uranium could be produced, and soon. Lawrence's response was immediate. Cyclotrons bent charged particles. Heavier particles curved less. Lighter particles curved more. That was basic physics. What if uranium atoms were ionized, given an electric charge, and sent through a powerful magnetic field? Uranium-235 would curve slightly more than uranium-238. Their paths would separate, catch them in different collectors. A mass spectrometer. Scaled up until it became an industrial machine. To most physicists, the idea sounded absurd. Mass spectrometers were laboratory instruments, delicate, slow, precise. Scaling one to factory size seemed impossible. Lawrence did not wait for consensus. He ordered his 37-inch cyclotron modified into an experimental separation device. The machine would later be called a Calutron, a contraction of California University Cyclotron. On December 2, 1941, 5 days before Pearl Harbor, Lawrence powered it on. It worked. Not efficiently, not cleanly, but unmistakably. By January 1942, the crude prototype had produced 18 micrograms of uranium enriched to roughly 25%, 10 times higher enrichment than any previous method had achieved. To most scientists, this was insignificant. To Lawrence, it was proof. Proof that the physics was sound. Proof that separation by mass could work. Proof that scale, not theory, was now the primary obstacle. And scale was Lawrence's specialty. He immediately began sketching designs for machines hundreds of times larger than the prototype. Rooms filled with Calutrons, racetracks of magnets bending uranium beams day and night, miles of coils, massive power supplies. That was when the success of the Calutron revealed its hidden cost. Magnets. Huge magnets. Magnets so large and powerful that they would consume more conductive metal than any civilian facility had ever used. Copper was the obvious choice. It was the standard conductor. It was reliable. It was everywhere. Until it wasn't. In 1942, copper was the lifeblood of the war. Ships, aircraft, radios, radar, ammunition. Every branch of the military was consuming it faster than it could be mined and refined. The War Production Board rationed it ruthlessly. Even critical programs struggled to secure enough. When engineers calculated the copper required for the electromagnetic separation plant planned for Oak Ridge, Tennessee, the number stunned them. 5,000 short tons, just for the magnet windings. There was no supply, no workaround, no substitute. Except one. Silver, the most electrically conductive metal on Earth. Silver could carry even more current than copper. 11 units of silver could replace 10 units of copper. The efficiency was slightly better. The problem was scale. Silver did not exist in industrial circulation. It existed in vaults. And that realization sent Kenneth Nichols back to the Treasury. This time, with a number no one in Washington had ever heard spoken aloud. 14,700 tons. And with that request, the assumption that national wealth was untouchable finally collapsed. The decision to melt thousands of tons of national silver did not come from extravagance. It came from a system under pressure. Scientific, industrial, and strategic, strained to its limits by a single, brutal requirement: uranium-235. By early 1942, the Manhattan Project's physicists agreed on one immutable fact. An atomic bomb could only work if its core contained uranium enriched far beyond anything found in nature. Not slightly enriched, not moderately enriched. At least 90% uranium-235, preferably more. Everything else was noise. Natural uranium was overwhelmingly useless. Out of every 1,000 atoms, only 7 were uranium-235. The remaining 993 were uranium-238. Chemically identical, physically similar, and functionally inert for bomb design. No chemical process could distinguish between them. No filter could sort them. No catalyst could favor one over the other. Chemistry was helpless. Physics was the only remaining tool. That reality shaped every decision that followed. It was the reason the Manhattan Project became an engineering program as much as a scientific one. It was the reason timelines mattered more than elegance. And it was the reason unconventional solutions were not just tolerated, but encouraged. The fundamental challenge was deceptively simple to state: separate atoms that differed only in mass. Uranium-235 weighed slightly less than uranium-238. That difference, 3 neutrons, amounted to a fraction of 1%. But in physics, even small differences could be exploited, if you were willing to pay the price in scale. Several approaches competed for attention. Gaseous diffusion was theoretically sound. Convert uranium into uranium hexafluoride gas, force it through porous barriers, and lighter molecules would pass slightly faster than heavier ones. Repeated thousands of times, enrichment would slowly increase. The problem was materials. Uranium hexafluoride was corrosive. The barriers required pores measured in millionths of an inch. No material existed that could survive long enough while maintaining uniformity. Even minor imperfections ruined the process. Thermal diffusion offered another path. Temperature gradients could drive isotope separation, but the method was unstable, inefficient, and poorly understood at scale. It might supplement other methods, but no one trusted it as a primary solution. Centrifuges were elegant. Spin uranium compounds at high speed and let centrifugal force separate heavier isotopes from lighter ones. In theory, it was efficient. In practice, early centrifuges were fragile. Bearings failed, rotors shattered, vibration destroyed alignment. It was a promising future technology, not a wartime one. Each method had merit. None offered speed with certainty. Against this backdrop, Ernest Orlando Lawrence stood apart. Lawrence was not interested in incremental improvement. He believed in brute force physics. If a process worked in principle, he would scale it until it worked in practice. His laboratory at Berkeley was famous for machines that grew larger, heavier, and more powerful with each iteration. Where others refined equations, Lawrence ordered steel. The cyclotron was his masterpiece. By accelerating charged particles in circular paths using magnetic fields, Lawrence had already demonstrated that mass controlled motion. Lighter particles curved more sharply. Heavier ones resisted bending. That principle was not theoretical. It was operational. He had built machines around it. When British physicist Mark Oliphant arrived in Berkeley in 1941 with news from the United Kingdom's atomic research committees, Lawrence listened closely. Britain believed a bomb was possible, Oliphant said, but only if enriched uranium could be produced quickly. The implication was clear. Whoever solved enrichment first would decide the war's endgame. Lawrence's mind moved immediately to the cyclotron. If charged particles could be bent, then charged uranium atoms could be bent. If they bent differently, they could be separated. The device would resemble a mass spectrometer, but on a scale no one had attempted. The idea was not refined. It was not efficient. It did not promise elegance. It promised speed. Lawrence did not wait for approval. He ordered his 37-inch cyclotron dismantled and rebuilt. The new configuration would ionize uranium, accelerate it, and send it through a magnetic field strong enough to force separation by mass. Collectors placed at precise locations would capture different isotopes. On December 2, 1941, the modified machine was powered on. The timing was extraordinary. 5 days later, Pearl Harbor would drag the United States into war. But on that quiet December day, Lawrence's team watched as ionized uranium traced curved paths inside the machine. The result was unmistakable. The beam split. Heavier uranium-238 curved less. Lighter uranium-235 curved more. Tiny amounts of material collected in separate cups. It was crude. The yields were microscopic, but separation had occurred. By January 1942, the prototype had produced 18 micrograms of uranium enriched to approximately 25%. That number meant nothing to bomb designers. 18 micrograms could not power a reaction, let alone a weapon. But to Lawrence, the number meant everything. It proved the principle. For the first time, the Manhattan Project possessed a method that demonstrably separated uranium isotopes. It did not matter that it was slow. It did not matter that it was inefficient. Speed could be bought with numbers. Efficiency could be sacrificed for output. The only unforgivable failure would be a method that did not work at all. Electromagnetic separation worked. The Calutron, short for California University Cyclotron, was born. Almost immediately, Lawrence began pushing for scale. He envisioned hundreds of Calutrons operating simultaneously, arranged in oval racetracks. Each racetrack would contain dozens of vacuum tanks, each bending ion beams day and night. Uranium would flow continuously. Enrichment would accumulate incrementally. It was an industrial vision built on laboratory physics. The Manhattan Project's leadership listened cautiously. Other methods were still being pursued in parallel. No one wanted to bet everything on Lawrence's machines. But as alternatives struggled with materials, reliability, and time, the Calutron gained momentum. Then, reality intervened. Scaling electromagnetic separation exposed a problem that physics could not solve: magnets. The Calutron's magnetic field had to be powerful, stable, and uniform. Small laboratory magnets were manageable. Industrial magnets were something else entirely. The coils had to be enormous. They had to carry tremendous current. They had to operate continuously without failure. The obvious material was copper. Copper was the backbone of electrical engineering. It was abundant, workable, and well understood. Engineers began calculating how much copper would be required to build the magnets for the planned Y-12 electromagnetic plant at Oak Ridge. The answer stunned them. Approximately 5,000 short tons. Not for the entire plant, for magnet windings alone. In 1942, 5,000 tons of copper might as well have been 5,000 tons of gold. Copper was being consumed faster than it could be replaced. Ships, aircraft, tanks, radios, radar systems, power grids, every element of the war effort depended on it. The War Production Board rationed copper with ruthless efficiency. Even critical weapons programs faced shortages. The Manhattan Project was still secret. It could not simply demand priority without explanation. Even if it could, the copper did not exist. The project faced a paradox. The only proven enrichment method required magnets. Magnets required copper. Copper was unavailable. Without magnets, the Calutron was dead. Without the Calutron, uranium enrichment might fail entirely. It was at this moment that the system sustaining the Manhattan Project revealed its most uncomfortable truth. Success would not come from optimizing within constraints. It would come from violating assumptions. One engineer asked a question no one else wanted to ask. What if copper were replaced? Steel was useless. Aluminum could not handle the current. Brass offered no advantage. Only one metal surpassed copper in electrical conductivity: silver. Silver conducted electricity better than any other metal on Earth. 11 units of silver could replace 10 units of copper. From a purely electrical standpoint, it was ideal. From every other standpoint, it was absurd. Silver was not an industrial metal. It was a monetary reserve. It existed in vaults, not factories. Using it for magnet windings meant melting it, reshaping it, stressing it, and exposing it to damage. It meant treating national wealth as raw material. The idea seemed insane. And yet, when engineers ran the numbers, no alternative remained. If the Calutron was to live, silver had to replace copper. That realization sent Lieutenant Colonel Kenneth Nichols back to Washington, back to the Treasury, back to the guardians of a resource that had never been touched for industrial use. This time, the number he carried was no longer shocking. It was incomprehensible. The moment Ernest Lawrence proved that electromagnetic separation could work, the Manhattan Project gained something it had been desperately lacking. Not certainty, momentum. For the first time, uranium enrichment was no longer an abstract problem waiting on theoretical breakthroughs. It was a machine problem. Machines could be built. Machines could be multiplied. Machines could be forced to operate faster than elegance allowed. But machines obeyed physics, and physics demanded payment. The Calutron prototype at Berkeley had worked because it was small, forgiving, and isolated. Scaling it up meant dragging laboratory physics into the unforgiving world of industrial reality, where tolerances tightened, failures multiplied, and every assumption was tested under load. This was where the system began to fracture. Lawrence envisioned calutrons arranged in enormous oval formations he called racetracks. Each racetrack would contain dozens of separation tanks, all operating simultaneously. Uranium ions would flow continuously. Enrichment would accumulate gradually, pass after pass. On paper, the concept scaled beautifully. In practice, it collided head-on with engineering limits. The first fracture appeared in the magnets. A calutron's performance depended almost entirely on the quality of its magnetic field. The field had to be strong enough to bend heavy uranium ions. It had to be stable enough to keep their paths predictable. And it had to be uniform across large volumes of space. Laboratory magnets were manageable. Industrial magnets were not. Each full-scale calutron magnet required massive coils capable of carrying extremely high current for extended periods. The coils could not overheat. They could not warp. They could not fail. Engineers calculated the dimensions. Then they calculated the current. Then they calculated the amount of conductive metal required to carry that current safely. That was when the numbers stopped making sense. To build the magnets for the WWII electromagnetic plant at Oak Ridge, the project would need approximately 5,000 short tons of copper, just for the windings. This was not a margin. It was a minimum. 5,000 tons. In 1942, copper was not merely scarce. It was strategically critical. Every battleship relied on copper wiring. Every aircraft generator. Every radio. Every radar set. Every shell casing. Copper was embedded in every layer of modern warfare. The War Production Board rationed it aggressively, redirecting supplies constantly to meet shifting priorities. Factories fought for allocations measured in pounds. The Manhattan Project was asking for thousands of tons. Even if the project had been declassified, and it could not be, there simply was no copper to give. This was not a procurement delay. It was a structural impossibility. Without copper, the magnets could not be built. Without magnets, the Calutrons were useless. And without Calutrons, the Manhattan Project risked losing its only enrichment method that had actually demonstrated success. The system that had sustained the project, parallel approaches, redundancy, theoretical diversity, began to narrow dangerously. Time compounded the pressure. Intelligence on German atomic progress was incomplete, but what little information existed was alarming. German physicists were competent. Germany had access to uranium. No one could say with confidence how close they were to enrichment or weaponization. The Manhattan Project could not afford to abandon a working method simply because it was inconvenient. That realization forced a re-evaluation of assumptions that extended far beyond physics. One of those assumptions concerned materials. Copper had always been the default conductor for large-scale electrical systems. It was abundant. It was cheap. It was familiar. Engineers reached for it instinctively. But copper was not the best conductor on Earth. Silver was. Silver conducted electricity approximately 6% better than copper. That difference was marginal in consumer applications. In massive electromagnetic systems operating at the edge of thermal and electrical limits, it mattered. Engineers ran the substitution calculations reluctantly. If copper were replaced by silver, the total mass required would increase slightly, roughly 11 units of silver for every 10 units of copper. For the Y12 magnets, that translated to approximately 5,500 tons of silver. The number was horrifying. No industrial supply chain could produce that amount. No mine, no refinery, no warehouse. There was only one place in the United States where thousands of tons of pure silver existed in uniform, controlled form. The United States Treasury. Specifically, the bullion reserves stored at the West Point Bullion Depository. Silver that backed currency. Silver that belonged, in theory, to every American. Silver that had never been treated as raw material. Suggesting its use for industrial magnets bordered on sacrilege. The idea circulated quietly at first, almost as a thought experiment. Some assumed it would be dismissed immediately. Others believed it might be used temporarily, with full recovery afterward. Kenneth Nichols did not treat it as hypothetical. As the Manhattan Project's chief of construction and logistics, Nichols understood that physics did not negotiate. If the Calutrons needed silver, then silver would be required in physical form, not metaphorical form. Bars would have to be moved, melted, reshaped, installed, and eventually returned. The proposal moved upward through the project's leadership, stripped of emotional language and framed in engineering terms. Silver was not being spent. It was being borrowed. It would be tracked to the troy ounce. Losses would be minimized. Recovery would be mandatory. The logic was cold. The implications were staggering. This was the first time the Manhattan Project forced the federal government to confront a choice between preserving monetary orthodoxy and pursuing wartime necessity. The fracture widened when Treasury officials began asking questions that could not be answered. What would the silver become? How long would it be gone? What risk was acceptable? Nichols could not explain. The project's classification prevented disclosure. The Treasury was being asked to relinquish control of national wealth to a program it was not allowed to understand. This was not merely a logistical problem. It was a philosophical one. For generations, American monetary policy had rested on the assumption that precious metal reserves were sacrosanct. They existed to stabilize the economy, not to be consumed by it. War had already bent many rules. This one would break them. As negotiations continued, the scope of the requirement expanded. Engineers refined their designs. The Calutrons grew larger. Additional racetracks were added. Redundancy was built into the layout. Each revision pushed the silver requirement higher. 6,000 tons became insufficient. 7,000 was still short. 10,000 failed to cover contingencies. By the time the final designs stabilized, the number no longer sounded real. 14,700 tons. 14,700 tons of silver would be required to wind the magnets for the Y12 plant. At that scale, the operation ceased to resemble borrowing. It became transformation. The silver would have to be melted in secure facilities, cast into billets, extruded into long strips, and transported across multiple states under guard. It would pass through hands that had never handled precious metal. It would be stressed by currents powerful enough to tear tools from workbenches. It would be exposed to heat, vibration, corrosion, and wear. Every ounce would have to be accounted for. Every filing, every shaving, every particle. The Treasury understood what this meant. Once approved, the decision could not be undone. The silver would vanish from vaults and reappear as something unrecognizable, industrial infrastructure embedded deep inside a secret city. For the Manhattan Project, this was the point of no return. They had moved beyond theory, beyond prototypes, beyond conservative engineering. They were now asking the nation to convert wealth into weaponry, not metaphorically, but literally. When Nichols prepared to return to the Treasury with the final number, he knew the request would sound insane. But insanity had become irrelevant. Only one question mattered. Would the system bend, or would it break? The second time Kenneth Nichols walked into the United States Treasury, the number no longer shocked anyone. It stunned them. 14,700 tons of silver. Not a proposal, not an estimate, a requirement. By the summer of 1942, the Manhattan Project had crossed a threshold from which there was no retreat. The Calutron was no longer an experiment. It was the only uranium enrichment method that had demonstrated real separation. Every alternative remained theoretical, fragile, or years from readiness. The project could not afford to wait for elegance. It needed mass. It needed current. It needed magnets. And magnets demanded metal. Copper was gone. Silver was all that remained. Inside the Treasury, the logic was evaluated with the same discipline applied to monetary policy. Every bar of silver stored at West Point weighed exactly 1,000 troy ounces, approximately 31 kilograms. Each bar was logged. Each bar was audited. Together, they represented more than accounting. They represented trust. Melting them meant crossing a line that no American institution had crossed before. The Treasury's first concern was not ideology. It was accountability. If the silver left the vaults, it had to come back. Not approximately, not mostly. Every troy ounce. Nichols understood this immediately. He agreed to conditions that bordered on absurd. monthly accounting down to the fraction of an ounce, recovery of shavings, filings, dust, storage of rags, incineration of floor sweepings, chemical extraction of residue from waste materials. The Manhattan Project accepted every requirement without hesitation. This was not negotiation. This was survival. The approval process moved quickly, quietly, and without public record. No announcement was made. No justification was offered. The transfer of one of the largest concentrations of precious metal in the world began under armed guard. The silver did not move as treasure. It moved as freight. Train after train departed the West Point Bullion Depository, carrying uniform bars stamped with serial numbers and purity marks. Guards accompanied every shipment. Logs tracked every transfer. No bar disappeared without documentation. The first destination was Carteret, New Jersey, a defense plant corporation facility capable of handling large-scale metal processing. Here, the transformation began. Furnaces roared. Bars that had never been altered since casting were fed into crucibles and reduced to molten metal. Liquid silver poured into molds, forming cylindrical billets, intermediate shapes designed not for storage, but for deformation. In that moment, the silver ceased to function as money. It became material. From Carteret, the billets moved south to Bayway, New Jersey, to the Phelps Dodge facility. This was one of the few plants in the country capable of extruding metal to extreme dimensions with consistent quality. Under immense pressure, the billets were forced through steel dies and stretched into long, gleaming strips. Each strip measured approximately 0.625 inches thick, 3 inches wide, and dozens of feet long. The dimensions were precise. Deviations were unacceptable. Silver in this form no longer resembled wealth. It resembled industrial muscle. In total, 258 railcar loads of silver strips left Bayway. Each shipment documented to the fraction of a troy ounce. The strips traveled next to Milwaukee, Wisconsin, to Alice Chalmers. This was where the silver would be transformed into something unprecedented. At Alice Chalmers, engineers wound the strips onto massive mandrels, layer by layer, forming coils of extraordinary size and mass. Each coil weighed many tons. Ordinary cranes strained to lift them. The process was slow, methodical, and unforgiving. Once wound, each coil was sealed inside a welded steel casing. These casings served multiple purposes. They protected the silver. They provided structural integrity. And they concealed the metal itself. Once sealed, the silver vanished from view. Painted steel boxes replaced gleaming metal. To anyone watching from a rail platform, they looked like ordinary industrial equipment. No guards, no markings, no indication of value. The illusion was deliberate. Flatbed rail cars carried the finished magnet assemblies south to Tennessee, to a valley that did not exist on any public map. Oak Ridge. By the time the silver arrived, Oak Ridge was no longer a construction site. It was a city. Bear Creek Valley had been chosen for isolation, not beauty. Surrounded by ridges, it offered natural containment. If something catastrophic occurred, an explosion, a magnetic failure, a criticality accident, the terrain might limit the damage. The Y-12 electromagnetic plant dominated the valley. 825 acres, nearly 80 acres of indoor floor space. Power stations, cooling towers, machine halls, maintenance shops. At its center were the Calutron racetracks. From above, Each racetrack formed an oval hundreds of feet long. Inside, rows of vacuum tanks lined the curve. Each tank weighed approximately 14 tons. Around each tank, the silver-wound magnets wrapped like metallic muscle. These were not elegant machines. They vibrated, they hummed, they resisted control. Inside each vacuum tank, uranium tetrachloride was vaporized, ionized, and accelerated. The ion beam entered the magnetic field generated by the silver coils. Heavier uranium-238 curved less. Lighter uranium-235 curved more. At the far end, collectors waited to capture faint smears of enriched material. On paper, the process was simple. In reality, it was violent. The magnetic forces involved were enormous. Tools left too close to the magnets could be ripped from hands. Tanks shifted under load, drifting inches out of alignment. An inch was enough to destroy beam focus. Humidity attacked the coils, causing shorts. Heat warped collectors. Impurities, what operators called gunk, condensed inside the vacuum chambers, clogging apertures and scattering beams. Nothing behaved the way laboratory physics predicted. Engineers fought back. They anchored tanks more securely. They redesigned supports. They added cooling systems. They developed new cleaning procedures. They improvised tools and protocols that did not exist in any manual. And through it all, the silver had to be protected. Paper was placed beneath every drill point to catch filings. Oily rags were collected, stored, and later burned to recover residue. Even the floors beneath the machines would eventually be torn up and incinerated to extract microscopic particles. Nichols filed monthly reports to the Treasury with military precision. Every ounce was tracked. Losses were unacceptable. This was engineering under siege. By late 1943, it became clear that the Calutrons could not be operated efficiently by scientists alone. The machines required constant adjustment. Tiny deviations in needle readings could ruin hours of work. Immediate response mattered more than understanding. The solution came from an unexpected source: operators. Tennessee Eastman was contracted to staff the plant. Thousands of young workers, mostly women from rural communities, were recruited and trained. They were not taught physics. They were taught discipline. Keep the needles in the green. Turn this knob if it drifts. Turn that knob if it drifts the other way. Do not ask why. To the surprise of everyone involved, production improved. Physicists hesitated, analyzed, theorized. The operators reacted instantly. When needles drifted, corrections were immediate. Stability improved. Output increased. When Lawrence doubted the reports, a controlled test was arranged. Scientist versus operators. Same machines, same time window. The operators won decisively. Execution had beaten understanding. By early 1944, the Calutron system, battered and temperamental, was finally producing enriched uranium at a meaningful scale. The silver magnets were holding. The impossible decision had not collapsed the system. It had saved it. By early 1944, Oak Ridge had crossed another invisible threshold. The question was no longer whether electromagnetic separation could work. The question was whether it could work fast enough. The Calutrons were finally producing enriched uranium in quantities that mattered. But the margin for failure remained razor thin. Every hour of downtime meant lost material. Every misaligned beam meant wasted energy. Every mistake echoed forward through the entire enrichment chain. What had become clear was that Oak Ridge was not winning because of perfect machines. It was winning because it had learned how to adapt faster than its own failures. The Alpha racetracks came first. Their job was not to create bomb-grade uranium. Their job was to take natural uranium, where U-235 made up only 0.72%, and push that number high enough to make the next step possible. Tenfold enrichment was considered a success. Anything more was a gift. The beta racetracks came next. Here, tolerances narrowed brutally. Collector slots were thinner. Beam paths were tighter. Magnetic stability mattered more than raw power. A fluctuation that an alpha track could tolerate would shut down a beta machine instantly. This two-stage system, alpha feeding beta, was fragile by design. But it was the only path that existed. Every gram of uranium passed through the system multiple times. Each pass concentrated value and risk. Inside the Y-12 plant, time ceased to behave normally. Operators worked in shifts around the clock. Machines never truly rested. Maintenance crews slept in fragments. Engineers lived with clipboards and stopwatches, measuring drift, logging failures, rewriting procedures as fast as reality invalidated them. And slowly, painfully, the system began to stabilize. Not because the machines improved, because the people did. The Calutron operators, the young women recruited by Tennessee Eastman, developed an instinctive relationship with their control panels. They learned the personalities of individual machines. They knew which units drifted left under heat, which ones surged after cleaning, which magnets demanded constant attention. They were not allowed to know what uranium was. They were not told what enrichment meant. They were taught only outcomes. If a needle moved, they moved it back. That discipline became the quiet backbone of the entire operation. By mid-1944, production logs told a story that numbers alone could not capture. Yield per hour increased. Downtime decreased. Recovery rates improved. The Calutrons were still temperamental, but they were no longer unpredictable. The machines had not changed. The system had learned how to live with them. The Manhattan Project leadership took notice. General Leslie Groves had never trusted elegance. He trusted results. Oak Ridge was finally producing them, slowly but measurably. At the same time, other enrichment methods were advancing. Gaseous diffusion, once dismissed as impractical, was beginning to show promise. But it was not ready yet. Not in time. Not at scale. For the bomb that mattered most, the first one, Oak Ridge remained indispensable. Every shipment of enriched material leaving Y-12 traveled under secrecy so tight that even its handlers did not know what it was. Small containers, greenish compounds, numbers without labels. Those containers moved west to Los Alamos. There, scientists waited. By late 1944, calculations shifted. For the first time, it became mathematically plausible that enough U-235 could be produced for a single weapon. Not comfortably, not with margin, but enough. Pressure intensified. Germany surrendered in May 1945. For Oak Ridge, the war did not slow. The Pacific conflict remained unresolved, and the timeline compressed brutally. Every gram mattered. By the summer of 1945, Oak Ridge had achieved the unthinkable. Approximately 64 kilograms of uranium enriched to roughly 80% U-235 had been produced. It was not ideal. It was not efficient. But it was sufficient. That material became the core of a weapon unlike any built before. Little Boy. On August 6, 1945, at 8:15 a.m., the B-29 bomber Enola Gay released the uranium gun-type bomb over Hiroshima. The explosion released energy equivalent to approximately 15,000 tons of TNT. An estimated 70,000 people were killed instantly. Tens of thousands more would die in the months that followed. 3 days later, a second bomb fell on Nagasaki. On August 15th, Japan surrendered. World War II ended. At Oak Ridge, the reaction was muted. There were no celebrations inside Y-12. Many workers were not told what they had done until after the surrender. Some felt pride. Some felt shock. Some felt guilt. Many felt all three at once. The machines that had consumed their lives were suddenly unnecessary. And with that realization came a final obligation: the silver. From the beginning, the Treasury had been clear. Every ounce had to come back. Now the war was over, and the reckoning began. The Calutrons were shut down. Racetracks that once vibrated with power fell silent. Control panels went dark. The machines that had pushed physics to its limits became inert steel. Dismantling began. Casings were cut open. Silver coils were unwound carefully, strip by strip. Years of heat and stress had darkened the metal, warped it, twisted it. Each piece was cleaned, weighed, logged. Nothing was discarded. Collectors were removed, vacuum tanks cleaned, every surface wiped, every rag saved. Floors were torn up and burned. Ashes were sifted. Chemical extraction recovered particles invisible to the human eye. The work took years. Kenneth Nichols continued filing monthly reports to the Treasury, now tracking recovery instead of allocation. The numbers crept upward, ounce by ounce. Out of approximately 430 million troy ounces loaned, all but 155,645.39 troy ounces were recovered. Less than 0.036% loss. For an operation involving molten metal, rail transport, massive electromagnetic forces, corrosive chemicals, and constant mechanical failure, the result was astonishing. The Treasury accepted the final accounting. The debt was closed. A final footnote lingered. 67 tons of silver remained in service as industrial components until 1970. Only then were they replaced with copper and returned to storage. The Calutron era ended quietly. But its consequences did not. Oak Ridge did not disappear. Y-12 evolved into the Y-12 National Security Complex, responsible for maintaining components of the United States nuclear arsenal. The valley remained a cornerstone of national security. The Calutrons themselves became obsolete almost immediately, replaced by more efficient methods. But their principle lived on. Mass spectrometry, ionize, bend, separate by mass, became one of the most important scientific tools of the modern age. Medical diagnostics, environmental monitoring, planetary science, forensics, all trace a conceptual line back to silver coils in Tennessee. What began as desperation became infrastructure. What began as an absurd request became precedent. The United States had melted its wealth to buy time, and time had been enough. When the last Calutron racetrack went dark, there was no ceremony, no speeches, no flags, no acknowledgement that one of the most extreme industrial experiments in human history had just ended. The silver was leaving Oak Ridge, quietly, crate by crate, coil by coil, rail car by rail car. The metal that had once formed the electromagnetic heart of the Manhattan Project began its long return to the Treasury vaults. The machines that demanded it were already obsolete. The urgency that justified them had passed. but the world they helped create could not be dismantled so easily. The Calutron system had been built for a single purpose: produce enough uranium-235 for one bomb. It was never intended to be efficient, economical, or sustainable. It was a bridge across an impossible gap in time. And it had worked. The uranium shipped from Oak Ridge to Los Alamos became the core of Little Boy, the only uranium gun-type atomic bomb ever used in war. Unlike the plutonium implosion device dropped on Nagasaki, Little Boy had never been fully tested. There was not enough enriched uranium to waste on a trial. Its success depended entirely on Oak Ridge. Without the Calutrons, there would have been no uranium weapon in 1945. Without that weapon, the war's final chapter would have unfolded very differently. But the strategic consequences extended far beyond August of that year. The first and most immediate consequence was doctrinal. Oak Ridge proved that industrial scale could be forced onto problems previously confined to laboratory benches. Isotope separation had been a precision science, slow and delicate. The Manhattan Project turned it into factory labor. That lesson reshaped post-war engineering. Complexity no longer disqualified an idea, it merely demanded organization. The second consequence was institutional. Oak Ridge did not disappear after the war. The valley that had once hidden silver-wound magnets became a permanent fixture of American national security. Y-12 evolved into the Y-12 National Security Complex, responsible for manufacturing and maintaining components of the United States nuclear arsenal. The mission changed, the secrecy did not. The third consequence was technological. Although calutrons were rapidly abandoned in favor of gaseous diffusion and later centrifuges, the physics they embodied survived. Ernest Lawrence's principle, ionize particles, bend them with magnetic fields, separate by mass, became the foundation of modern mass spectrometry. Today, mass spectrometers diagnose diseases, detect environmental contaminants, analyze forensic evidence, and study the chemistry of distant planets. They operate on the same idea that once demanded 14,700 tons of silver to sustain. The scale shrank. The impact grew. The fourth consequence was psychological. The Manhattan Project demonstrated that a nation at war could justify decisions previously unthinkable. Melting down national treasure was not efficient. It was not elegant. It was not reversible in principle. It was urgent. The silver loan revealed something fundamental about modern warfare. When timelines compress far enough, wealth becomes material, not meaning. The Treasury did not defend its silver because defending it would have cost time. And time was the one resource the project could not replace. Perhaps the most overlooked consequence, however, belonged to the people. The Calutron operators, mostly young women, many barely out of high school, were never told what they were doing. They were trained to follow indicators, not ideas. They kept needles steady without knowing what those needles represented. Only after the war did many of them learn that their shifts had shaped the atomic age. Their role challenged assumptions that expertise alone determines outcomes. At Oak Ridge, execution mattered more than understanding. Discipline outperformed theory. That lesson unsettled the scientific hierarchy of the time. It also quietly redefined what skilled labor meant in the modern industrial state. The return of the silver closed the final ledger. Out of approximately 430 million troy ounces loaned, more than 99.96% was recovered. The loss, less than 5 tons, was absorbed without protest. Some metal had vaporized, Some had bonded, chemically beyond recovery. Some simply vanished into the margins of industrial chaos. The Treasury accepted the accounting. The promise was kept. By 1970, the last remaining silver components were replaced with copper and returned to storage. The transaction that had once seemed impossible was complete. 14,700 tons borrowed, 14,700 tons returned. On paper, the balance was restored. In reality, the world was altered permanently. Oak Ridge stands today as a reminder of what happens when engineering, secrecy, and urgency converge. It is a monument not to genius alone, but to coordination, discipline, and the willingness to attempt what logic says should not be attempted. The Calutrons are gone. The silver is gone. The war is gone. But the age they enabled remains. The atomic age did not begin with a mushroom cloud. It began quietly, in a Treasury office, when a young officer asked for a number no one could fully comprehend. And the nation decided that melting its wealth was an acceptable price for ending a war.